conference on quantum technology. So just to give you a very brief
Recording in
introduction.
progress.
Yeah, so welcome to all the participants. So just a quick introduction. I am Srinath Raman. I'm director at Capital Logic. And we are a boutique advisory firm advising on various disruptive technologies or deep technologies. And in fact, way back 3 years back, I was a participant in the very first quantum conference that was organized in India, the Indo-Quant, which also happened to be in Hyderabad. This was in early 2019. And I tracked this industry very closely from a business standpoint. As you know, this is a very fast-moving industry. This is the industry of the future. And therefore, the purpose of this particular presentation would be to give an idea of what the current status is. There have been a lot of developments over the last, particularly over the last 2 or 3 years. This whole quantum technology industry is where the classical electronics industry perhaps was in the late 70s or 80s. And this is going to be the industry of the century, right? So with that, let me just start off. I am also, by the way, part of the advisory committee on quantum for Telangana state. So let's kick things off. Yeah. So if you can, these are a few quotes, and I'm sure many of you would have been familiar with some of these, and you've got a sense of what quantum and the impact of quantum has been over the recent years, over the recent decades, and particularly about how it will transform the world over the next century. So for example, people have called it the century defining technology, which means that the 21st, 22nd century will be really the quantum century, and that quantum could even be as transformational in the 21st century as electricity was in the 19th, which really started off the whole industrial revolution. Many of you might know that in the 1970s and 1980s, quantum, one of the fathers of quantum was Richard Feynman, the very famous physicist. And he actually proposed that in order to model and simulate the underlying physics, as you know, the underlying physics at the atomic level is all quantum. And therefore, to simulate physics at the quantum level, we should be having quantum computers as opposed to the classical ones that we currently have. And one can actually pay homage to Richard Feynman's for his visionary kind of thoughts. And today, 40 years later, we are on the verge of this entirely transformational industry. Now, what are just at a high level, and I'm sure you would know many of this, some of the very pressing problems that globally the world is looking to solve, right? Whether it be in the area of computer vision, cybersecurity, energy, supply chain optimization, drug discovery, which is extremely important so that we can make sure that diseases can be conquered, all the diseases that take a huge number of lives, all of that can hopefully one day very soon be eliminated. We are talking about computational fluid dynamics, which would enable very accurate weather forecasting, right? So if we can model the dynamics of the way the stratospheric changes happen in the atmosphere and so on, that would really lead to very extremely accurate weather forecasts. So all of these can be enabled using quantum computers. And just to give you a sense, again, as you may have perhaps listened to from various speakers over the last couple of weeks, there are 3 broad areas where quantum technology is increasingly used, right? So quantum computing, quantum communications, and quantum sensing. And let me start with perhaps the lesser known one, which is quantum sensing. And you can use quantum technologies to build ultra sensitive sensors, right? These sensors, because essentially quantum technologies and quantum principles like entanglement, superposition, tunneling, these are extremely, extremely sensitive to environmental factors. And therefore, any change in environmental conditions can be extremely quickly modeled or sensed using these quantum sensors, much more so than any other kind of sensors that we have today. And what are the things that can be sensed? Anything. I mean, today, even atomic clocks are a huge area, right? Even today, they are a big area where quantum sensing is used, even to detect gravity, for extremely sensitive measurements of gravity, electromagnetism, various other areas, right? And these are orders of magnitude. So we are talking about 10, 100, even 1,000 times more sensitive than classical sensors. Next, we come to quantum communications, and I'm sure many of the speakers would have talked about the fact that with quantum computers coming in, there is a very real possibility that all of our current cryptographic techniques and principles can be broken, right? And therefore, the very critical information that is shared every day on quantum, on our regular networks, can be hacked into by hackers once, let us say, quantum computers come in. And therefore, to prevent that, what is required is quantum cryptography or quantum secure communications. And this would become the basis of secure transfer of quantum information across space, right? And this is unbreakable in the sense that this is based on the laws of physics. Like I said, on the laws of quantum physics, entanglement, superposition, and therefore, if any eavesdropper were to try and hack into and get the information that is going over some of the wires, that would be automatically detected by these quantum secure communication technology, essentially QKD, and we're going to talk a little bit more about that in the next slide. And so that is a very important application of quantum communications. And of course, the most important, the third one, is really quantum computing. And this leverages the laws of quantum mechanics to provide, we are talking about exponential performance improvement for even some of our very, very hard and challenging classical problems, problems that we face using our best supercomputers, as well as we are talking about addressing certain kinds of problems which no supercomputer, no classical computer in the world today can address today, nor can they ever in the future, because we are talking about simulating or modeling the core atomic energy levels and so on, right? Which today is frankly impossible even for any classical computer. So, just very quickly, before I dive into some of the details of the various hardware and software developments that have taken place over the last few years, just to give you some numbers on you see the quantum computing side, quantum communication side, and the quantum sensing side. And these are numbers that McKinsey, the leading global consultant, has come up with. So if you see in terms of number of players or startups who are working on these sectors, or the total startup funding, or the estimated market size a decade down the road, a decade or two down the road, really the order seems to be quantum computing is the highest in terms of startups, or the amount of startup funding, the market size. So we're talking about 10 billion to 100 billion kind of numbers of market size. Quantum communications would be next, and finally we are talking about quantum sensing. So the idea out here was just to give a sense of the huge growth that we are seeing in this industry, which there is a very high likelihood that this would replace the entire classical information technology industry, which was spawned from the 1970s. Right, so classical computing was ruling over the last, let's say, 50 years, and going forward, it's all going to be, that's so there would be, let's say, the next couple of decades where both classical and quantum would exist, and as and when we see a clear quantum supremacy and quantum advantage established, the playing field is going to tilt more towards quantum computing. Just to complete on the quantum sensing and quantum communication side before we enter into the main topic, we talked about quantum sensing. So we are talking about bioimaging, spectroscopy. So anywhere in any domain where you want to sense at a ultra sensitive level, right? So when you're doing bioimaging, we want to know perhaps even at a cellular level or at a biomolecular level, what is wrong in the human body, what is really causing the disease. And with these ultra sensitive quantum sensors, right? Today, IoT, as many of you might know, is ensuring that there are sensors across the world, right? Sensing all kinds of environmental factors, or sensing various aspects deep within the human body. And with these quantum sensors, the sensitivity can be multiplied many-fold, 100,000, that's what we talked about. And you can use this for various aspects. Even when you're talking about communication, you want to sense the radio waves. In navigation, you want to sense the exact location. GPS today is only to about 3 meters square. But if you want to make it much more accurate, you can use quantum sensing for environmental monitoring. Let's say how much of carbon dioxide is in the atmosphere precisely. If you want to detect mechanical issues in various structures, if you want to survey where exactly there is oil and gas found deep within the ground. So that kind of geographical surveying, obviously very much in fundamental science. All of these are areas where quantum sensing can be used. On quantum communication, some of the big areas, as many of you perhaps might have heard from the other speakers, the basic one is quantum cryptography or quantum encryption. And again, quantum key distribution is the leading method today. So what basically happens is that if you want to secure the communication, you exchange keys, the sender and receiver exchange keys, and so that the keys would encode the information that you are sending, and at the other end, the receiver would decode the same information using the keys. And so what we are doing with quantum key distribution is that we are not encoding the actual information. The actual information would be encoded, but it would be encoded using classical mechanisms. But the key distribution, so you need to distribute the key so that the person at the other end can decode the information. And the key distribution would happen in a quantum way, which means that there is no scope for it to get hacked at all. And then, of course, for doing this, quantum random number generators are extremely important. Today in computing, we use a lot of classical random number generators, but they're not really, you can prove theoretically using mathematics that they do not really provide real random number generation, and therefore quantum RNGs are superior. The other factor is that these quantum signals, they attenuate very rapidly, and therefore you need these quantum repeaters every short distances so as to amplify these quantum signals. And increasingly, it is not just, as you know, all of quantum communication is based on photonics technology, right? You are applying quantum principles in the photonics domain. And these can be done for land-based networks, and in the future, it will also be based on satellite transmission of radio waves, right? And therefore, we are talking about extremely long-distance quantum networks. We are talking about the quantum internet. So potentially, the landline-based internet today can be replaced with quantum principle-based internet, which was perhaps streamed through these satellites, right? So moving on. Overall, the quantum communications market is also increasing extremely rapidly. We are talking about $1 billion in market size very soon. Right now, the banking and finance industry is one of the largest end users, simply because there is a lot of financial information which is extremely sensitive, and you need to protect that kind of information from leakage or from the threat of hackers, right? You don't want hackers to hack into your bank account and take away all your money, and therefore, the financial industry is expected to be, and already is, one of the biggest users of quantum secure cryptography or quantum secure communications. And of course, the government and military sectors, right, where you're talking about extremely sensitive information, are going to be amongst the other big users. And with the boom in IoT, with the boom in cloud storage, there's a lot of data security concerns. So with all of this, the need for quantum cryptography has just exploded. There are a lot of players in this space. As you can see, there is also an Indian player, which is fairly active, operating out of Bangalore and Hyderabad. So, as well as obviously some of the very big players internationally, like ID Quantique, which is based in Switzerland, Magic Technologies, etc. So now we come to the core and the interesting part of this session, where we delve into the core quantum computing aspect, right? And what have been some of the recent developments on the various hardware and software approaches. So particularly focus, this slide, if you see, is quite important. We have had multiple approaches. So you see the approaches on the top that have been used. Superconducting qubits. We also have ion trap based qubit technology. At the end of the day, all of these various approaches have to generate quantum bits, which are called qubits. But then the way they are generated and what kind of it differs, right? So superconducting qubits use extremely, almost at absolute zero, superconducting material to kind of generate these qubits. Photonics uses some, as you would appreciate, light and photons for this. And right now, the predominant approach has been superconducting qubits for, let's say, the last couple of decades or so. Having said that, if you see the survey at the top, and we are talking of a survey of some of the leading global experts in this space, and what do they consider which technology is promising? So 61% still say superconducting qubits. The next big one and the next two, which are very close, are ion trap technology and photonics. And this is very interesting. Even, let us say, when I did my last session about 3 years back, superconducting qubits was number one, ion traps was a close number two, and photonics was supposed to be a distant number three or number four. And so what has happened in the interim is that photonics has actually made up huge ground. And now people, a lot of experts are even talking about after superconducting qubits, they're all talking about photonics, and it may very well happen that perhaps photonics even takes over at some point in the next few years as perhaps the leading technology. Having said that, we at this point in time cannot take a guaranteed kind of position as to which one of these will for certain win out. As of today, the leading one is superconducting qubits. Then there is both ion traps and photonics based qubits are there. So the biggest companies in this space, if you take the superconducting qubits, we are talking about IBM, we are talking about Google, and we are talking about a pure play firm called Rigetti Technologies, which is very prominent in this space. If you're talking about ion traps based qubits, we are talking about Honeywell. We are talking about a firm called IonQ. Those are the prominent firms. For photonics, the two kind of biggest startups in this space are a firm called PsiQuantum, which is headquartered in London, and is a spin-off from Imperial College of London. And then there is an American firm called Xanadu. And surprisingly, and I will come to that fact also on another slide. So the pure, as you know, IBM, Google, Honeywell, these are all public listed companies, very large companies. These are big tech firms. These pure plays, Rigetti, IonQ, these have gone public only in the last year, 2021. So 2021, we saw the first instance of some of these pure play quantum firms getting listed in the global markets. So in America, right now, Rigetti, IonQ, both are listed. They are about $1.5 to $2 billion in valuation, right? We are very recently, there is a firm called D-Wave, a Canadian firm, as many of you might know, which has a technology based on quantum annealing. And the difference there is that quantum annealing, they are the leaders in the whole quantum annealing based hardware. Quantum annealing is not regarded by most experts as being your equivalent to the ultimate qubit-based quantum computing. However, for many challenging optimization problems, it can actually act as well as traditional quantum computers that are being built, let's say, by IBM, Google, Rigetti, etc. Having said that, they may not be able in the future to address the very deep chemistry and biology-based simulation problems and challenges that ultimately the quantum computers, we expect them to address. Having said that, for these very challenging optimization problems, D-Wave is a very, very significant player today, and which is playing in the quantum annealing space. So D-Wave has also just filed, and they are going to go public in the US markets. They have filed already for their IPO, or actually they will be going public under a route called a SPAC, and they will also be valued at around 1.5 to $2 billion. PsiQuantum, which is perhaps the leading firm in the photonics-based quantum space, it is valued at actually above these firms. It is still private, but about $3 billion as per its last valuation. So it just goes to show that a lot of people are betting on photonics potentially as perhaps being the leading technology a few years down the road. If you look at these various, one other thing that I would like to mention, that Microsoft is pursuing a very interesting approach called topological quantum computing, and that is recognized to be a much more longer term kind of play, right? So unlike, let's say, IBM or even Google, who are coming, IBM has been perhaps the most proactive, and they have been responsible for establishing a lot of the research and patents and development in this space consistently over the last 2 decades. Google has been close behind. There have been a lot of announcements from these firms over the last several months and years. Microsoft has been taking a much more longer term view, right? But it may very well be that a few years down the road, their approach may perhaps result in much more fault tolerant computing. The goal, as many of you might know, is that fault tolerance, or these qubits are very prone to errors. They are prone to decoherence, and therefore they are alive and they last only for a few nanoseconds. So if you look at the comparison on the second row, the qubit lifetime, right, for superconducting qubits is 1 millisecond. For ion traps, it is around 50 plus seconds. For others, it is a few seconds, right? And then the more important part is the gate fidelity in terms of errors. Almost all of them today have are in the region of 99% plus gate fidelity. In terms of gate operation time, though, the superconducting qubit is the best. So it's around 10 to 15 nanoseconds, right? As opposed to ion traps, which is around, let's say, between 1 to 50 microseconds. And so the problem, though, with the superconducting qubits is that they require near absolute zero temperatures. And as you can imagine, that takes a lot of energy, that will make them expensive. And but what is happening is that year over year, we are seeing extremely strong performance improvement in all of these. Going along, just to summarize, right? If you talk about which are the tech majors who are most active, who are coming out constantly with new announcement, among the tech majors, the tech biggies or big tech, IBM, Google are very active. At the next level of tech challengers, among the biggies who have taken slightly different approaches, but over the long run, it is very possible that they may win out, right? Are Microsoft and Honeywell. And if you look at the pure play firms, those who are not really big tech are, as you know, IBM, Microsoft, Honeywell, Google, they are into multiple areas, into classical supercomputers, normal computers, into the software side, etc. But here, the next 2 rows, we are talking about pure play quantum machines. And here the leaders are the current leaders, like I mentioned, Rigetti, IonQ, D-Wave Systems, PsiQuantum. And interestingly, each one of them has taken a different approach. So Rigetti is focused on superconducting qubits. IonQ has taken the ionic route for generating qubits. Like I mentioned, both of them recently got listed. D-Wave Systems is into quantum annealing. PsiQuantum is taking the photonics route. And all of them, the first 3 right now, the valuation are about $1.5 to $2 billion. PsiQuantum is about $3.2 billion. And then there are obviously many other firms that are coming up. Xanadu is also playing in the photonics based quantum space. There is Cold Quanta, which is taking a very different approach, right? It was also mentioned in the previous slide of cold atoms. There is another firm called Quera. So these are some of the major players who you will increasingly hear about as we go into the future. Now I'm going to share some of the roadmaps that each one of these major players are talking about. And I will start with IBM, because IBM in many ways, I would say, is the most mature and a leader in quantum technologies. And if you look at it, IBM, as of last year, you see the second row from the bottom, they have achieved 127 qubits. Year before that, it was 65 qubits. Year before that, it was 27 qubits. So in 2 years, it's been a 10x jump, right? And they are forecasting that they will reach 1,000 qubits by 2024 in another 2 years, right? Now, having said that, the number of qubits is important, but the other aspect which is very, very important is also the fault tolerance and the error correction capability of these qubits. And that is also something that all of these players are working on. On top of the hardware, you can see the status of on the software side of quantum computing. So just above the hardware, we have something called the quantum circuits that one needs to develop. As you know, IBM has come out with their quantum SKD and the programming language called Qiskit, right? And they have, so Qiskit is one of the more popular ones. There are also ones from Google, etc. And so that is at the kernel level that you can see out there. And in the future, Qiskit will be used for the runtime. It will be used to build dynamic circuits, for circuit libraries, and so on. On top of the circuits would come the quantum algorithms for various domains, whether you're talking about the natural sciences, you're talking about finance, you're talking about machine learning. And as many of you might know, and I will talk in a further slide, machine learning enhanced with quantum is probably the most exciting space today, right? It is an amalgamation of AI with quantum. So you're mixing together two of the most exciting areas within computer science today. And on top of that would be coming out with the actual models. So when we are talking about simulating and coming out with models for biology, for how your biomolecules, DNA, proteins, how they actually function at a very, very minute and micro level, or if you're talking about how chemistry works and how atoms actually interact, to really understand how they work today, you need to be able to model and simulate all of this. And so you will increasingly need a lot of model developers. Those kind of positions today until 2023 or 2022, this year and next year, are not really there because we have not gotten to that stage. But from next year, that will also start to happen, right? So this is to give you a sense of the roadmap of IBM. Next, we move on to Rigetti. Like I mentioned, Rigetti is the leading pure play firm which is focused on superconducting qubit technology, right? And Rigetti, as of 2021, has about 80 qubits. And this itself is a doubling of what it was the year before. And they also say there's just about, let's say, a year behind IBM, though of course from a qubit standpoint. But there is a big debate whether this is apples to apples comparison, because one firm says, okay, I have done 100 qubits. Another firm also says, yes, I have also done 100 qubits. Can you really compare this apples to apples? Like I said, the fault tolerance and error correction aspect is equally important. So Rigetti also says that by 2024, they will reach about 1,000 qubits. And we will come to this whole aspect of proving what is called quantum supremacy or quantum advantage. And the very exciting development that is expected to happen. As many of you might know, Google in 2019 announced that they had proven quantum supremacy. What that really means is that they haven't proven a particular use case where no classical computer, the biggest supercomputer in the world now or in the future, will be able to solve that kind of problem in reasonable time frame. But whereas a quantum computer can very easily solve that kind of problem, right? Ultimately, what everybody is interested in is to prove that when can we see a particular solution that will that you can prove and say classical computing can never approach what quantum computers have done in this space. So Google claimed that it had achieved this in 2019. There is, as in any of these kind of players, there were some various debate about that. And China is increasingly one of the biggest players, more so on the quantum communication side, a little bit less on the quantum computing side. But even China, only was it last year or so, they claimed that they had also achieved, one of the leading universities out there also claimed that they had achieved quantum supremacy, which means that for a very niche kind of problem, they demonstrated that quantum computers could come out with a solution in, let's say, a few minutes, which the best supercomputers, classical supercomputers, would take many years to come up with that kind of similar solution. So anyway, we will talk more about the whole aspect of quantum advantage. So they call it either quantum supremacy or quantum advantage. Nowadays, quantum advantage is the more preferred term. We will come to that. So this is the roadmap for Rigetti. Here we are talking about the quantum roadmap for IonQ. As you can see, it's a very exciting space. So all of these big players, IBM, Google, Rigetti, IonQ, PsiQuantum, Xanadu, they're all competing against each other to develop more qubits, more reliable qubits, and ultimately trying to prove that these are the kind of problems that can be tackled, which no traditional supercomputer or the best classical computers can tackle. Now, so IonQ right now is somewhere around 30 qubits, but their qubit definition is a little bit different, which is what, like I mentioned, in some of these areas, you really cannot compare apples to apples. Having said that, they claim that their qubits are much more fault tolerant, and therefore their 30 qubits would be more equivalent to, let's say, 100 qubits of some other provider. That is their claim. Now, we will come to what are the kind of applications that is possible. The biggest, most of these providers are expecting that over even currently and over the next couple of years, the biggest area where there will be impact of quantum computing is, like I said, in this mixture of machine learning and AI with quantum computing, right? So it is quantum machine learning that we are talking about, and this is the hot area. Also, there is a lot of progress in terms of optimization, traditional supply chain optimization problems in finance and various other kind of areas, which are already happening and will happen at a faster rate over the next few years. Having said that, the simulation of chemistry, atoms, biomolecules, which many folks expect, many experts expect that would be the biggest bang for the buck for quantum computing, which means that we will essentially discover the mysteries of life and of chemistry, and maybe perhaps even eliminate diseases and down the road. So, but that is the major kind of quantum computing that enables all of that is expected to happen, let's say, 2 or 3 years down the road. So this is the roadmap from IonQ, as you can see. So just to summarize a few points about the quantum computing industry landscape. First point is that of these various hardware paradigms, there is a very intense competition going on at this time, a very interesting competition. At this point, it is not yet clear which quantum computing hardware paradigm will be the eventual winner, though superconducting qubits is definitely the leading one currently, right? Photonics quantum computing has made immense strides, especially over the last 2 or 3 years. And that is reflected in the fact that PsiQuantum, which is the leading photonics-based startup, has the highest market valuation of all the pure play quantum players at around $3.1 billion as per the latest funding round. Whereas even Rigetti and IonQ are more in the $1.5 to $2 billion range, right? And PsiQuantum has also announced plans for a commercially viable 100+ qubit photonic quantum computer by 2026. Now, of course, we will have to wait and see if they can realize that. And the interesting thing is that quantum hardware technology, we are in the early stages. It is growing at rates. You saw some of the rates, right? Well above Moore's law, which means the law which determines the rate at which classical computers have been improving their performance. We even saw 10x improvement in hardware technology over the last 2 years for quantum side, right? And even going forward, if you look at the roadmap of all of these various providers, we are talking about doubling of qubits estimated every year, right? Which is huge. Classical computing has more or less plateaued out because we are seeing, as many of you might know, the death of Moore's law. Again, like I mentioned, IonQ, Rigetti, both got listed last year, which is speaking to the fact that all investors are pumping in money into this space. D-Wave is expected to go public over the next few months. So that is about this entire quantum computing landscape. Coming to what I talked about of quantum advantage. So both Google claimed that quantum supremacy or quantum advantage was proven. Having said that, they claimed this for some very niche kind of areas. What everybody would like to see is in a very practical application, a relevant problem that can quantum computers show that they are able to come out with a solution which no classical computer would be able to do, and that is very much expected. That is what the entire industry is working towards. And whereas at a theoretical level, as well as the level of niche problems, this has already been proven by Google, by Chinese university, right? Now we are waiting for this to be proven in a practical, operationally relevant problem, and we expect, the industry players expect that by next year, let's say around 2023, the narrow quantum advantage would very probably be done and proven at around that time period. And by around 2025 or so, broad quantum advantage, right, which would be solve a practical problem which would be physically impossible to solve on any classical computer, however powerful it eventually becomes. That would also be proven, let's say, by 2025 timeframe. Now, as you can see at the bottom, over the last few years, quantum computers have predominantly been used on the R&D side of things. Increasingly, it has already started that it is being used for quantum machine learning, right? And as you can see in those colored bars out here and out here, the biggest use case today and till, let's say, 2025, other than the R&D side, would be quantum machine learning. And from around 2025 onwards, we are expecting that both quantum simulation, as well as even today, there's a lot of optimization that is going on with these quantum computers, but that will also start taking off big time, and that is expected to happen around the 2025 timeframe. So going forward, this was also mentioned in our the heading. So this era is called the NISQ era, right? The noisy intermediate stage quantum phase. And why is it called that? As you know, qubits, the biggest issue right now is that they are not fault tolerant, they are error prone. And with the exponential growth of quantum technology, we do expect that this NISQ era will end, which means that we would have perfectly fault tolerant and error correcting quantum circuits, but that is still a few years down the road. In spite of that, so if you take the most conservative estimate, the very most conservative estimate, that may happen by 2030. As per the most optimistic estimates, it could even happen next year, 2023. And therefore, in that particular range, is when really the expectation by experts is that NISQ era will last at least for the next 2 or 3 years. But even within this NISQ period, what is happening is that all the investment is growing exponentially. A lot of investment is happening, and therefore it makes practical sense for many of you who are in universities. This is going to be the technology of the future, and for you it makes perfect sense to invest your time, your effort in learning these technologies, right? And that is what will perhaps give you the dividends in terms of very perhaps extremely high paying jobs and so on as we go over the next several years. I will not go into some of the actual industry sizes out here, which is more for the business folks. And moving on, IBM, like I mentioned, which has been taking a very a strong leadership role in the development of the whole quantum industry, they have actually looked at what kind of metrics can be used to benchmark quantum performance. So one is, just in terms of number of qubits. But another very important aspect is what is called quantum volume, right? And quantum volume tries to combine both the metrics of quantum number of quantum qubits as well as the quality of the qubits in terms of how long do these qubits last, and is the fault tolerance there or the error correction there. And therefore, it is really a sense of how many quality qubits has the provider managed to put in place. Right? So quantum volume in many senses may be a better indicator than pure number of qubits. And then, of course, like in classical computing, we are talking about clock speed and flops. Here, we are talking about CLOPS, clock, circuit layer operations per second, right? The number of circuits, quantum circuits that can be run on any hardware in a given time. So these are various benchmarking tools or metrics that are used for the quantum side. Now, so this slide is also very interesting. From a theoretical perspective, it has already been proven, right? So many of you might know about P and NP, right? So P and NP represents all the set of all problems that are solvable in polynomial time, essentially which are solvable quickly by classical computers. And NP is the ones which are not solvable or are solvable in non-polynomial time or maybe even exponential time. And therefore, they may take years to even solve these kind of problems, right? And if you look at the left-hand side out here, these are the set of all problems, whether quickly or taking many years, that are solvable by classical computing. And there is a set of problems called, and BQP is the bounded quantum polynomial time space. So there are problems, it has been proven, which can never ever be solved by classical computers, however fast they are made, even let's say today or 10 years or 20 years or 30 years down the road. And you can prove using theoretical computer science and theoretical math that there are certain problems that are only solvable by quantum computers, and this has been proven. So the theoretical proof has already come. When we are talking about quantum supremacy or quantum advantage, we are waiting for the practical actual demonstration. Even out there, like I said, even that has been demonstrated for some very niche and kind of problems, which would normally, and very scientific kind of problems. What we are now only waiting for is for this demonstration to happen for some very practical and impactful problem that, right, which can be used by industries today. And that is expected to happen in the next couple of years or so. Very quickly moving to the software side of things, you might know about this. Each one of these players has come out with their own SDK programming language. So on top of the hardware, typically you have the assembly language, you have they give a framework for building the circuits, the quantum circuits in the case of quantum computers, and then the language for building the quantum algorithms. Then on top of that, the full stack libraries. And then there are even open source, like you have an open source movement in classical software. There is increasingly an open source movement which is not linked to any particular hardware provider, right? So we are talking about open source quantum universal languages. And as you know, IBM Qiskit is its language which addresses all of these various hierarchical modules. Rigetti has its own. Google CIRQ, CIRQ is one of the other major ones. Microsoft has its own language called QHash. And so each one of these players have their own software stack built on top of the hardware components. And as most of you would know, today, because of cloud computing, most of these even the hardware as well as the software and simulators of quantum circuits, all of them are accessible over, let's say, the major cloud providers. We are talking of Amazon, or we are talking of Microsoft, right? The big cloud providers. So they increasingly, you can access all of them through the, you can access Qiskit, you can access quantum simulation languages, and you can access IBM's quantum hardware or Rigetti hardware or D-Wave over these cloud platforms. Finally, we already talked about this. So what did we talk about? We are talking about which are the major application areas where we see opportunity, right? So cryptography more related to the quantum communication side. So quantum cryptography is going to explode in a very big manner, and therefore all of you who have backgrounds in, let's say, theoretical computer science, in mathematics, in statistics, all of these set you up very well, extremely well, to do extremely well in the cryptography space, and that area is going to explode. Encryption, decryption of the communicated messages. For quantum computing, the three big areas, like I said, one is quantum machine learning, the next is quantum simulation, and the third area is quantum optimization. And in the longer term, it is estimated that quantum simulation will perhaps, both in terms of demand for people, in terms of qualified resources, in terms of the market size, in terms of the impact that it may have on the world and industry. The biggest hopes are on quantum simulation, where we will know ultimately the secrets of all of the biomolecules that constitute all of life, that constitute each and every one of us, or how these atoms combine with each other in chemistry. Having said that, the quantum simulation is still not at a very developed stage today and for the next couple of years, and it will really start. See, this whole space is growing exponentially, and many of us can't really imagine what exponential growth really means, right? So today it might barely be visible, but it is going to hit you like a truck in a couple of years' time. So all of this is going to dramatically change the entire landscape. Quantum machine learning is already big, and quantum optimization. When we are talking about quantum optimization, we are talking about applications in weather forecasting, in climate forecasting. We are talking about aerospace, route optimization. We are talking about a lot of applications in finance, in market, in risk management, in market prediction, in portfolio optimization. We are talking of all of your traditional supply chain optimization, vehicle routing, etc. So these are areas under the optimization category. In machine learning, wherever today you're using, machine learning and AI in a big way, whether you're talking about computer vision, automated vehicles, self-driving, you're talking about your e-commerce, high-tech search, etc. So all of them can be further optimized by using machine learning. And when you have these big parameters, AI, and today they're very costly, and they also result in a lot of energy use. And it is even expected that quantum, first of all, would make it much faster in terms of training all of these machine learning algorithms. And at the same time, even the kind of the climate aspect and reduction in energy usage, etc., is another big advantage. And of course, like I mentioned, in simulation, we are talking about chemistry, we are talking about biomolecules, we are talking about battery design for electrical vehicles, and so on. So I will not spend much time on the market sizes. I mean, those are for the business folks. And summarizing again, these are the key big application areas. You're talking about simulation, optimization, machine learning, cryptography. And so I think we have spent enough time on talking about these different aspects. It is a very exciting time, I think, for anybody who is in university today or just starting out in the job market. And definitely, whether you can get into formal programs in quantum area, or you can do learn up on quantum on the side through these various programs that are available, you should definitely think of doing that, because this will really add an edge to anybody, any one of you who's investing the time and effort to do this. Finally, I will just end with a couple of interesting slides, and this is from McKinsey in their very recent report that has just come out a few months back. So there are two, this slide and the subsequent slide. And if you see this slide, what it talks about is that this is a ranking of countries done by McKinsey. So it is a very kind of authoritative report by the amount of talent available in different countries for, this one was specifically for quantum. As you know, India has traditionally been strong in terms of talent for various kinds of software technologies, whether you're talking about traditional software, whether you're talking about advanced other AI or IoT, and we see that the same is happening even on the quantum side. So in fact, India has the highest number, about 150,000. Of course, when you translate it into density, given that India is obviously one of the largest ones in terms of demography, so from that perspective, therefore, India actually lags, let's say, the European Union or the US or the UK, etc. But still, I think this is a very good metric, and I think India should be proud of it. Having said that, if you look at this next slide, and this is a ranking of countries by McKinsey by patents in the quantum space. And as you can see, as of now, India does not even figure in the top 10. China, as you know, China is one country that, it keeps a focus and, it wants to achieve, become the number one in various different disruptive technology categories. And they have taken a conscious decision. The maximum number of papers, patents, etc. today are increasingly coming out from China. Of course, China's focus is a little bit more on the quantum communication side as opposed to the quantum computing side. And if you look at the traditional quantum computing side, the US and Europe and Canada, etc., still have some of the market leading firms. But China is very focused. But the point here is that India needs to translate its advantage in terms of demography and talent pool to try and figure out here, we need to have more patents, we need to have more startups in this space, right? See, what will happen is that all these companies, the big companies, IBM, Microsoft, Rigetti, IonQ, over the next several years, they will all get started to be attracted to India to leverage its talent pool. So that's a very good opportunity, very good sign for India. Having said that, we also want to have a number of startups. We want to have patents in the space from India. And ultimately, that's what we would hope that many of you out here would be doing. You have an opportunity to work with some of the best firms. You also have an opportunity to establish startups and hope to create this entirely new kind of technology that is going to be transformative for the world. And that is about. I hope this presentation that was it. It covered all the material that I had, just to give you a sense of the dramatic changes that have been happening in this industry. Right, there have been tremendous changes even over the last couple of years, even since my last session a couple of years back. And it's very important for all of you to know this, know that this is exponential growth, and position yourself appropriately for the future. I did not, I think, get a chance to address many of the questions. Unfortunately, I think we are running out of time. There is, I believe, a session right after this where we will be taking on questions on the specific aspect of employability and other aspects, industry aspects, and perhaps we can address it there. Thank you very much to everybody. Thanks a lot.
Sir, on behalf of Photonics Valley Corporation, we would like to thank you, sir. And it was very informative, even with all of your statistics. It really showed us the path regarding how quantum computing is going to grow in the next 5 years down the line, next 10 years down the line. It was very informative. On behalf of Photonics Valley Corporation, we would like to thank you once again, sir.
Thank you. And a pleasure talking to all of you folks out here and the students who are interested in this area of quantum. Thanks a lot.
Sure. Students, will get back to you in 5 minutes. Exactly at 12 o'clock, there's going to be industry interaction session where industry representatives from many companies would be joining in. Thank you. నెక్స్ట్ సెషన్ మనకు 12 o'clock స్టార్ట్ అవుతుందమ్మా. ఏదమ్మా ఒక 5 minutes యాడ్ ఇచ్చుకుంటే మనకి ఎగ్జాక్ట్ 12 o'clock మళ్ళీ మనకు